Presentation we will look at how we can improve the flexibility of power generation in back pressure power plants. We'll start to look at this very basic back pressure power plant. We have two-stage district heat production here. So this looks a little bit different from what we are used to having, but basically there is nothing really fundamentally different going on. It's just that we not have the condenser here. We have the back pressure coming here. Then we have extraction for our extraction condenser. Here we have the green line, that's the district heating water, district heating consumers here. And our power plant cycle is very ordinary. So condensing pump, low pressure feed heater, de-aerator, feed water pump, and one high pressure feed heater. So everything very ordinary, just drawn in a little bit different shape so that we can fit everything here a little bit better. So when we look at this kind of construction, the drawback is that how much steam is coming through the turbine is fully determined by how much heat load we have here. So if we have, for example, a situation that we have very low heat load, but electricity is at a high price, we would want to produce as much electricity as we can, but we can't because this here says how much steam is coming to these condensers, and that restricts how much power this turbine can generate. So now we'll look at a couple of ways how we can improve the flexibility and how we can allow ourselves to produce more electricity in situations of low heat load. So option number one, kind of the simplest and in the sense also the most effective, is that we simply add a condensing turbine. So this is often called a condensing tail because it comes at the back end of the back pressure turbine. Simply a condensing stage which effectively converts our back pressure plant into something that is functionally equivalent of condensing power plant with extraction heat production. So usually in Finland there's always some kind of natural water supply nearby that we can use for cooling water supply, and then we can, at situations of low heat price, we always actually need to run some steam through this, but we can choose to run only very, very little. Why we need to always run some steam through it is because there is going to be friction at the shaft, and we have to put some flow through it to pick up the heat that is being generated so that we don't overheat the turbine. But we can run only very little steam with low price, and then when we have high electricity price, we run as much as the plant can produce and as much as the turbine can take. Now, drawback of this situation is that this is fairly expensive. So we have the very large turbine back end. We remember large volumetric flow rate means huge turbine, long blades, large casing. Then we have a very large condenser. We have seen those pictures in the lecture number 3. So we need to give a lot of space for the steam to be able to flow into the tube bundle. And then of course we have to build the cooling water supply, and all that is going to cost a lot of money. And it comes with the drawback that we always have to run some steam through it unless we build a separate shaft and generator, and then that's going to make it even more expensive. So basically it is always going to be on the same shaft. Now, a little bit cheaper, actually not a little bit, but a lot cheaper version of the same general idea is that we don't actually add anything to the turbine, but we simply add a way of artificially increasing our heat load when we want to. And we do it by adding an auxiliary cooler. So basically just a heat exchanger that we create an additional heat load with. So some supply water is run through the cooled heat exchanger and back into the return pipe, and we can again use the whatever natural body of water we have that would supply the cooling water. Almost all district heating networks in Finland have this available because this heat exchanger is a lot smaller and a lot cheaper than this heat exchanger, and that is the only additional component that we have. So it's so easy, simple and cheap way of adding a lot more flexibility that we usually want to have it. Now, drawback is that we don't get quite as much additional power generation with this one, because we only add to the amount of steam flow through this part of the turbine, and here we would also additionally get additional expansion, and this we don't get here. Then third option that we could add is a storage tank. So idea here is that we have a very large storage tank, and if electricity is expensive, then we run some of the supply water through here. We heat this water that is in the tank. We get to run more steam through the turbine to fulfill this additional load here, and then when the opposite is true and we have the situation that we have very low electricity cost, then we can, instead of wasting fuel to produce electricity and heat, well, heat is always usually the same price, but to produce electricity when we get relatively little profit from it, then we are unloading this tank. And this is fairly common. It's not that it would be anywhere near from every network, but these are becoming more and more common. They also have additional uses, so it's not only that we can play with electricity prices, but we can also use this kind of storage tank to balance the daily fluctuations of district heat load. So there's usually a spike every morning, and there's another spike in the evening when people come home, and we can load and discharge this kind of storage tank to balance those changes a little bit. So to summarize, condensing turbine, this is the very expensive option. To be profitable, we need to have consistently high electricity price. Many people these days don't trust this to be the case, so these are very often not installed, but they do exist and sometimes do get installed. We get the greatest addition of power generation at low heat loads, and we usually have to accept that because we are on the same shaft, we always have to run at least a little bit of steam through it. Auxiliary cooler, cheapest investment, higher condenser pressure than the condensing turbine, so we don't get as much electricity, but it's a very cheap way of getting some extra hours of our CHP plant in the spring and autumn time. And so basically, on one hand, we get to produce more electricity when the price is worth it, but we also get to extend the operating time of the CHP plant so that we don't need to fire up our heat-only boilers that produce heat with very expensive fuels quite so early, when we can create some additional load and we can extend the minimum load stoppage point a little bit further down the line. And then finally, heat storage tank. Cost-wise, it's somewhere in between. We get good amount of flexibility, and we get to balance the heat loads also a little bit. And one important point that I didn't mention in the previous slide is that in contrast to the auxiliary cooler and the condensing turbine, these both are dumping heat to the environment, so our overall efficiency goes down. But with the heat storage tank, there is only the heat losses from the storage tank, which is minimal and negligible compared to these two. So those are the main ways how we can add flexibility to the power generation of a back pressure district heating CHP plant.